Hello everyone, this is Ms. Page, and in this lesson we are talking about sum and difference identities. This is actually the second day. We're going to look at some other types of problems that traditionally we use our sum and difference identities to solve at a pre-calculus level. So one of the things, of course, that we already know is our Pythagorean theorem, which applies to right triangles, of which this is one, although its little right angle is not shown. And so remember that sine, cosine, and tangent are defined in terms of a right triangle. So when we are looking at using a sum or difference identity with non-unit circle angles, we generally fall back on those definitions of sine, cosine, and tangent in terms of the ratio of two sides of a right triangle. So here what we're looking at is another way of looking at our sine, cosine, tangent, and their reciprocal instead of terms of opposite over adjacent and opposite over hypotenuse and so on and so forth. We look at it in terms of more of a unit circle concept where a point on the terminal side of our angle has a coordinate x comma y with the vertex of the angle being at the origin of the x and the y-axis. So this is our x-axis, this is our y-axis, and so this point right here, its coordinates would be x comma y. And so the y becomes the side opposite angle theta prime, which is the reference angle for theta. So the sine, cosine, and tangent of angle theta are the same for theta prime. So sine, cosine, and tangent for theta prime are equal to the sine, cosine, tangent for angle theta. So y is our side opposite, r is the hypotenuse of this right triangle, and x is the side adjacent to this angle theta prime. And so over here, our opposite over hypotenuse has been now defined as y over r. For cosine, our adjacent over hypotenuse is now x over r. Our tangent of opposite over adjacent is now y over x. And then our Pythagorean theorem is now x squared plus y squared equals r squared. Now, this is a very traditional way of looking at it. You can still do the problem with your old basic understanding of knowledge if you draw a picture of the right triangle in the correct quadrant. So that's the strategy I'm also going to share with you guys. And again, remember that you can use SOHCAHTOA to make sure that you are doing the ratios for sine, cosine, and tangent correctly. So here, this for reference is our sum and difference identities. So some of the things we've talked about with the two sine identities, the sign is the same. So sine of a sum, we do a plus. Sine of a difference, we do a minus. And for the two cosines, it's the opposite. So if we have plus there, we have minus over there. And minus gives us a plus over there. The other thing is that for the two sines, it goes sine, cosine, and then cosine, sine. Sine, cosine, cosine, sine. And for cosine, the two cosines, it always goes cosine, cosine, sine, sine. Cosine, cosine, sine, sine. All right. So this is basically what we're going to, the strategy I'm going to use with you guys. We're going to draw reference triangles in the correct quadrant based on where the angle terminates, quadrant 1, 2, 3, or 4. And again, if you've forgotten, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4, and we'll be given a sine, cosine, or tangent ratio, so we can put those two values into our unit or into our triangle rather, and then we'll use our Pythagorean theorem to find the third side of our right triangle. We will then identify the identity to be used. It will tell us what we're trying to find, like are we trying to find sine of alpha minus beta, cosine of alpha plus beta. So we'll just figure out, okay, what identity is that going to be? And then we will then from there do our, basically what we did in the previous lesson. We'll substitute values from our triangles this time into the identity. We'll simplify and then write that final simplified answer. All right, so here is our first example. So notice what we're given. We're given sine of angle alpha. So we have no idea what angle alpha actually is. And for a problem like this, we don't need to know alpha. So what we have here, though, is that we know that angle alpha is between 0 and pi halves radians. So we have to understand that puts it into quadrant 1. We are also given the cosine of angle beta. Again, we have no idea what measurement beta actually is, nor do we need to know it. We are also told that angle beta is between pi and 3 pi halves radians. So we need to know that that puts it into quadrant 3. So again, for your unit circle, this is your 0 radians, pi halves, pi, 3 pi halves, and then coming back, that's 2 pi. So that's what we're looking at. 0 to pi halves puts us in quadrant 1. Pi halves to pi puts us in quadrant 2. Pi to 3 pi halves puts us in quadrant 3. And then 3 pi halves to 2 pi will put us in quadrant 4. All right, so the first thing we are going to do here is we are going to make ourselves triangles in the first quadrant for alpha and in the third quadrant for beta. So I have this angle in my, here's x and y axes. So I'm going to draw myself a triangle like so in my first quadrant. Super important that your hypotenuse is connected to the origin. Hypotenuse is connected to the origin. This is our angle alpha. And so now my sine of alpha is 5 over 13. Sine, remember, is opposite over hypotenuse, which is also technically y over r, but we'll just go with the basics. So opposite would be 5, and hypotenuse would be 13. So then we can use our Pythagorean theorem. Also, though, if you remember some of your Pythagorean triples, that could be very helpful in problems like this when we're working with these. For example, if you remember that 5, 12, and 13 form the 3 sides of a right triangle, then you don't have to use your Pythagorean theorem. You can just know, okay, that's going to be a 12. All right, we're then also going to do the same thing for angle beta, but angle beta is in our third quadrant. So remember, our hypotenuse has to be connected to the origin, and then we drop the other side to always to the x-axis. That's supposed to be a y. So this is technically our beta prime, but if you just wrote beta, that's fine. And we know that the cosine of angle beta is negative 7 over 25. All right, listen up. Super important here that we understand where that negative belongs. One of the things about these problems is that you must understand that the hypotenuse, which represents the radius of a circle, like the radius of the unit circle is 1 unit. We're looking at this representing the radius of a circle that's not the unit circle, but just a circle, where this point right here is on that circle. That hypotenuse, because it technically represents a radius of a reference circle, must be positive. So when you look at cosine as adjacent over hypotenuse, that hypotenuse has to be the positive 25. Can't make it negative. So that means that our side adjacent is a negative 7, like so. And that makes sense because that's your x, and x in this direction should be negative because it's to the left of the origin. Now the other thing is when we use our Pythagorean theorem, we have to realize this right here, which is our side opposite, is also y, and y is negative in the third quadrant. And so we need this to be a negative value also. Also, again, if you recognize 7 and 25 is 2 parts of a Pythagorean triple, then you don't have to use your Pythagorean theorem. It makes the work a little bit faster that way. So the third value that goes with this Pythagorean triple is 24. But again, because we're dealing with our third quadrant and this opposite side is y, it must be negative. So this is actually then a negative 24. All right, so now we're going to go to our identity. So we want to find the sine of alpha minus beta. So we are going to need to use that identity. So the sine of alpha minus beta is equal to sine alpha cosine beta minus cosine, or actually I guess it does sine, different ways to write it. The way this does, it does sine beta cosine alpha. So there's always a sine and a cosine of each angle. All right, so now we're going to take our triangles and apply our definitions for sine and cosine and write down the values. So sine of alpha, sine of angle alpha, would be our 5/13, opposite over hypotenuse. It's also given to us, but from the triangle's perspective. Cosine of beta would be our negative 7/25, adjacent over hypotenuse. This is times negative 7/25. We have a minus. Sine of angle beta would be opposite over hypotenuse. So that would be negative 24/25 times cosine of angle alpha, adjacent over hypotenuse, would be 12/13. Now, even if you could, say, reduce or cross cancel or something here in your products, don't, because you're going to have to combine these through addition or subtraction in the next step, and you want there to be a common denominator. So right now, you'll have that common denominator of whatever 13 times 25 is. All right, so we're looking at negative 35 over 325. We have minus, and then this would be a negative, and this will be 325 also. And 24 times 12 is 288. So we get a negative 288. Now, for these problems, it is okay if you use a calculator. All right, some of the numbers will get rather large. You won't always recognize your Pythagorean triples and know for certain what the third value is, so calculators would be allowed here. All right, so now what we're going to do is combine these two through addition. So of course we're looking at this right here becomes plus a positive 288 over 325. This is still, of course, negative. So we're looking at 288 minus 35, and that will give us then a final value for sine of alpha minus beta as 253 over 325, like so. All right, let's take a look at another problem. All right, so here we are looking at, we are given the sine of angle alpha as 3/5. We are told that alpha is between pi halves and pi radians. So that is going to put it into quadrant 2. We are told that the cosine of angle beta is 24/25, and that beta is between 3 pi halves and 2 pi. So that's going to put it into quadrant 4. All right, so we're going to start with our reference triangles. So for alpha in quadrant 2, again, remember the hypotenuse should be connected to your origin, and then your vertical side to the x-axis. And this in here is going to be our alpha. Technically, alpha prime, but that's okay if you just put an alpha. And so we're looking at sine of angle alpha is 3/5. So this would be 3 and this would be 5. For a Pythagorean triple here, the third number is 4. 3, 4, 5. It's a 3, 4, 5 triangle. But here's what can be tricky about these problems. We are in the second quadrant, and this side right here is x, and x in the second quadrant is negative. So we actually have to make it a negative 4. Then looking at angle beta. So angle beta is in the fourth quadrant. So here, that's my x, that's my y. Here's my hypotenuse. Drop my vertical side to the x-axis like so. So this is beta prime. And I know cosine is 24/25. So 24 would be my adjacent side, which is x. 25 would be my r radius, which has to be my hypotenuse. So again, if I know my Pythagorean triples, that's great. I can go ahead and do that. But I also have to realize that in the fourth quadrant, this side, which represents y, this will be a negative value. So it's a 7, 24, 25 triangle. So this will have to be a negative 7. So now we're going to take a look at what we want to find. So here we want to find the exact value of cosine of alpha plus beta. So now we need our identity. So we have the cosine of alpha plus beta. So that would be cosine alpha, cosine beta, minus sine alpha, sine beta. And now we are going to replace each of those 4 with the ratios that come from our triangles. So cosine of angle alpha, here's my alpha, would be adjacent over hypotenuse. So that's negative 4/5. Times cosine of angle beta, adjacent over hypotenuse, would be 24/25. Minus sine of angle alpha would be opposite over hypotenuse, which is 3/5. And sine of angle beta, opposite over hypotenuse, would be negative 7/25. So now I'm going to do my multiplication. Again, I'm just following order of operations here. So I have 4 times 24, or negative 4 times 24, so it's going to be a negative. And it's going to give me 96. 5 times 25 would be 125. Then I have minus 3 times negative 7 gives me negative 21 over 125. So again, I have this minus negative, which becomes plus positive. So I'm looking at this negative 96 plus 21. So I want to take 96 minus 21. But again, you can use a calculator. So we're looking at negative 75 over 125, our common denominator. This time, though, we should recognize that we can reduce this. There's a common factor of 25 here. And so our cosine of alpha plus beta in its simplest form or reduced form would be negative 3/5, like so. All right, your next problem is going to be a practice problem for you to try. So pause your video here and give this one a try. All right, let's take a look at the result. So in this particular problem, we're looking at, here's our alpha, or alpha prime, like I said, technically, in our third quadrant. And we know that sine opposite over hypotenuse. So remember, your hypotenuse should be positive, which means that this would have to be negative, which makes sense. That's your y value, and y in the third quadrant is negative. It's a 3, 4, 5 triangle, but again, the other side has to be negative because x in the third quadrant is also negative. For your beta triangle, beta is just in the first quadrant. Nicely, everything in the first quadrant is positive. And so cosine adjacent over hypotenuse is your 12 and 13, and this a 5, 12, 13 triangle. This shows the Pythagorean theorem, but again, they're both Pythagorean triples, so the better you know those, the easier the math here becomes. Then we use our identity, plug in our values, do the multiplication. In this case, we're adding two negatives together, and we should get negative 56 over 65. All right, let's take a look at another example. All right, now this one, again, we're doing something a little different here. Now we have the tangent of angle alpha, which is given as 12 over 5. We are told that angle alpha is between pi and 3 pi halves, so that is quadrant 3. And we are told that the tangent of angle beta is negative 3/4, and beta is from 3 pi halves to 2 pi, which is quadrant 4. Stay with me here because tangent problems are definitely a little trickier. So angle alpha is in our third quadrant. Again, here's our x and y axes. And our hypotenuse has to be connected to the origin. Drop your vertical to the x-axis. So this will be alpha prime. And we know tangent is opposite over adjacent. Now here's what's, again, this is why I said tangent can be a little tricky. So opposite would be here at 12, adjacent would be here at 5. But we are in the third quadrant. And in the third quadrant, both x and y are negative. So we need to make sure we make both of them negative. Notice a negative over a negative reduces or simplifies to a positive. So that's what we're looking at, the simplified version of tangent. The values themselves are both negative. Then this is a 5, 12, 13 triangle, and hypotenuse is always positive because in context here it actually represents the radius of a circle that point is on right there. All right, for our angle beta. All right, beta is in quadrant 4. So again, our hypotenuse connected to our origin, drop our vertical to the x-axis. So here our tangent is negative. So again, it's still opposite over adjacent, but we have to understand which of those would be negative in this quadrant. So this is our side opposite. This is our side adjacent. We have to realize in quadrant 4, it's y that is negative. So the 3 has to be negative. And this is a 3, 4, 5 triangle. Hypotenuse has to be positive. So we have 3, 4. Our hypotenuse becomes 5. All right, so now we are going to look at our identity. So the exact value of cosine of alpha minus beta. So the cosine of alpha minus beta will be the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. And now we're going to plug in our values from our triangle. So cosine of alpha, I forgot to put my little beta in there. Prime. All right, so for our alpha, cosine is adjacent over hypotenuse, so that's negative 5 over 13. Cosine of beta, adjacent over hypotenuse, gives us 4/5. It's times. And then sine of alpha would be opposite over hypotenuse, so negative 12/13 times sine of beta, opposite over hypotenuse, negative 3/5. So now doing our multiplication. So this gives us negative 20 over 65. Plus, and this would be a positive 36 over 65. So 36 minus 20 is 16 over 65. That's not going to reduce. And so that would be our cosine of alpha minus beta. Like so. All right, let's have you guys try a problem. There you go. Give this one a try. All right, let's take a look at the result. So for alpha, alpha is in the first quadrant where nicely everything is positive. And this Pythagorean triple, we haven't actually seen yet. This is an 8, 15, 17 triangle, but it is another Pythagorean triple, and everything is positive. Tangent of beta. All right, let's see how you did on this one. So beta is in quadrant 2. Tangent is opposite over adjacent, but in quadrant 2, it is x that is negative. And so the 7 this time has to be the negative number. 24 has to be a positive value. And then this is a 7, 24, 25 triangle. We've seen that one before. All right, and then your identity, plugging in each of your values for sine of alpha, cosine of alpha, cosine of beta, sine of beta, doing all your math, get a negative 416 over 425. All right, one more practice problem. Give this one a try. Pause here. Let's take a look at it. All right, so for this one, we have alpha is in quadrant 4, and we know the sine. And in quadrant 4, remember, hypotenuse is always positive, so these are a little easier because of that, unlike tangent. And so we're dealing here with negative 7 here, and then this is again a 7, 24, 25 triangle. Beta is in quadrant 2. And in quadrant 2, we would have adjacent and hypotenuse, and this is a 5, 12, 13 triangle. Then we're doing cosine of alpha minus beta, so that would be our identity. Plugging in our values, doing the multiplication, doing the addition, ends up with negative 323 over 325. All right, that is the last problem in this lesson. Give your assignment a try and have a great day.